Then it's time to get started with this Nordic Tech webinar. How to measure power consumption on the nRF9160 system in package. Today's host is me, Martin Lesund. I work as a technical marketing manager for cellular IoT here at Nordic Semiconductor. Some practicalities before we begin this webinar. The duration of this presentation will be around 45 minutes and 15 minutes with Q&A at the end. Questions are of course encouraged, so please type your question in the top of the right sidebar in this little question box. All questions are anonymous and try to keep them relevant to the topic. We will answer them towards the end. The chat, however, is not anonymous and should therefore not be used for questions. If you have any more questions after this webinar, please go to our developer zone, which we call Dev Zone, and we will address your questions there. A recording of this webinar will be available together with the presentation at webinars.nordicsemi.com. So here's the agenda for this webinar. We are going to start with an introduction to the nRF9160 system in package. Then we're going to talk about the different modes of the modem and the different modes of the application processor. Then we're going to showcase the online power profiler and how you can use this tool to estimate power consumption. And then we're going to use the power profiler kit to actually measure the power consumption on a real network. At the end, we're going to talk a little bit about how to optimize your design for low power. And then some questions and answers. So let's start with the nRF9160 system in package introduction. So here it is, the nRF9160 system in package. It's based on Nordic dual-core system on chip with its own ARM Cortex-M33 microcontroller unit for the application side, and also has its own multiband LTM and NB-IoT modem with GPS support. For the application side, you have your own dedicated 1 MB of flash, 256 kilobytes of RAM, and you have support for ARM Trust Zone, ARM CryptoCell 310. You have up to 4 SPIs, I2C, UART, the usual peripherals. And you also have PDM, PVM, and ECDMA, as well as timers, real-time counters, and PPI support, and of course the general purpose I/O pins. You have single supply voltage around 3 to 5.5 volts, and you see that the package size is 10 by 16 by 1.0.4 millimeters. For the application, so like I said, it has a small form factor. It includes all the power management IC on board. It has the RF fronted and also the passives and crystals already inside. It has of course ultra low power, average current around 18 microamps at 81.92 seconds for EDRX in idle mode. And you have this 2.7 microamps for power saving mode. When the modem goes to sleep for a very long time, it uses this power saving mode. The modem, it has support for LTM with release 13, and it has also support for NB-IoT release 13, and it's also release 14 compliant for NV2. It has a GPS receiver, and we support all the main bands around the world, so you have global coverage, and of course we have support for the typical power saving features, DRX, EDRX, and PSM. And we have the secure socket, TLS, DTLS, IPv4, IPv6 stacks on board. The SiP itself is also pre-certified system in package. I highly recommend to go into our homepage website, check out the certification page we have there, which is constantly updated with the latest information with regards to certifications. We have just released the nRF9160 system in package revision 2. This one improves an already best-in-class low power solution. It has significant power improvements compared to revision 1, and there are no changes on the pinout nor the form factor. The only changes is for your existing revision 1 designs is that you need to change one external capacitor. In the table here you can see some key numbers. So the first one is that we have the CPU running the core benchmark at 64 MHz from flash with our high frequency crystal plus cache. So compared to revision 1 we improved 24%. And the PSM floor current is 2.7 microamps, which is 33% better than revision 1. And the average current for EDRX 655 seconds is 6 microamps on LTM and 9 microamps on NVIOT. So we have an improvement of 33% and 18% compared to revision 1. On this slide, we compare the nRF9160 system in package revision 2 with 3 other modules on the market. And we can see by this table here that we beat the other modules in every possible way for low power. The reason for this is that we have 2 decades of experience with regards to ultra low power. We have made our nRF51 series, our nRF52 series to be ultra low power, and we have brought this experience into this nRF91 series. And we have built this system in package from the ground up to be ultra low power. Also this modem we have built up to be ultra low power, and we have our own power management unit inside this system in package. So we always optimize for low power. And if we can optimize someplace, we do it. That's why we just released this revision 2 version. And we also try to optimize our modem firmware versions when we can and applications when we can to try to tweak it even more. So as you can see from the top here, we can compare with the closest module, which is module A, with the Nordic Gen 2 for the PSM floor, and we can see that we are 91% better. We have 2.7 microamperes. And also the PSM event boot, we have 85% better. And for the EDRX interval for 81.92 seconds, we are 64% better. And for uplink, 180 kilobits per second, 23 dBm power output, we are 43% better. And there are 2 points that are that we have on our nRF9160 that the competitor does not have, is that we have a low power application MCU on board, as well as a highly supported embedded SDK with lots of samples and drivers that makes it really easy to get started. One thing that's really nice with having a low power application MCU on board is that you make your final design much smaller. You don't need several external devices, and you have all your support questions to one company. So you just, if you have any issues with the nRF9160, you just go on DevZone and we will help you out. So now it's time to look at the different modes the modem can be in. So here are the 3 different modes: the radio resource control connected, the radio resource control idle, and power saving mode. So in the RRC connected mode, you transfer the user data, you have high power consumption. Since you are synchronized, you need to be synchronized with the network, and therefore there are a lot of clocks enabled and running to stay synchronized. In the RRC idle mode, you are listening on the network. You can sleep for shorter intervals to save power using the EDRX feature. And in this mode, you have shorter downlink latency compared to power saving mode, where you turn off the radio completely and sleep for longer intervals to save power. So let us take a close look into the RC connected mode and RC idle mode. So on the right hand side here you can see a figure showing the current compared with the time, and we start with RC connected mode. You have the network sync at the beginning, then we have the RC setup, and then you have your data transfer. So the nRF9160 can send, for example, a UDP data to a server. And when you're finished sending the data, it will go into this inactivity timer, which is also called the RC inactivity timer. It is decided by the network. Some networks has a timer around, for example, 4 seconds, and another network has a timer around 10 seconds, for example. It's important to note what timers your network use, because this will affect power consumption. And when this timer has run out, you have this RC release event, and then you jump to your next mode. And in this case, it's the RC idle mode we jump to. Here, the device will sleep in between the EDRX intervals. You turn off the radio, and then you listen, and then you turn off and listen to check if the network has something to send to you. And it's important to note that we support all the timers in EDRX, idle DRX, from 0.16 to 44 minutes. Not all other competitors supports all the timers. And this is something you can request from the network, and the network can grant you these intervals. So if you increase it, you will have a longer latency, but of course you will have much lower power. The next mode is the power saving mode. So on the right hand side here you can see we have the RC connected mode and the PSM mode. So when you go in RC connected mode after a PSM interval, you have the network sync, and you also have the SIM sync. You have the RC setup, you have the tracking area update, and then you have your data upload. So you send your data, and then you go into this RC inactivity timer again. And when you get your RC release from the network, you go back to sleep. And in this PSM interval, you have around 2.7 microamps in average of current consumption. So you can save a lot of power to stay sleep for a very long time. And the sleep intervals is between 10 minutes up to 413 days in theory. And this can be requested by the device from the network. And it's up to the network to grant these intervals. The device can, of course, wake up at any time to send data. So if you are in a PSM interval and have some alarm going on from a sensor or whatever, you can wake up directly up to RC connected mode again and send this data to your server. After the end of each PSM interval, the modem needs to switch back to RC connected mode and send its tracking area update, or including the data upload if you want to. Longer PSM intervals results in longer downlink latency, and the device cannot be reached by the network in this time. And the floor current is much lower, and the floor current is lower in the PSM mode compared to EDRX in RC idle. Let us look into the different modes of the application processor. So the application processor modes are either it's on or in idle or entirely off. So the MCU will always automatically switch to idle mode when it has no task to perform. This is thanks to our Zephyr real-time operating system running on the device. And this is what our NCS, our nRF Connect SDK, is based on. The application processor operates separately from the modem because of our dual core implementation. In our table here, we can see some key numbers with the MCU on idle, modem in PSM mode with the real-time clock turned on. And here we can see we have this 2.7 microamps average. And when the MC is on idle and the modem is turned off with the RTC on, you have 2.2 microamps. And if you turn off the modem and the RTC, you will get 1.8 microamps with the MCU on idle. And when you turn MCU off and modem off with no RAM retention and you have a wake on the general purpose input or reset, you are drawing 1.4 microamps. So let us look into how you can estimate your power consumption using the online power profiler. This is the first online power profiler for cellular IoT, where you can estimate and optimize your nRF9160 designs for power consumption. In this extensive tool, you can configure settings, you can have your network setup, your sleep intervals, your data payloads, how much you're going to send to the server, and then you have this visualized power profile, where you can see the peak currents and the timing, also the average. It's quite nice to just hover over the different modes to check more details what's going on. For example, in the figure on the right hand side, you can see that we have hovered over the PSM mode. You can see what the floor current is, when it started, the length and the charge. So since this tool is so extensive, we have a nice user guide that shows you how to use it. And a new feature with this online power profiler is that you can export the settings you have and add those to the UDP sample in our nRF Connect SDK. Then you can actually compare your estimation with the real current measurements that you get on your real network. So as long as you have the correct network setup in the power profiler, you should get the same results in the measurements. Now we are going to look into how you can actually measure the power consumption using the Power Profile Kit 2. So this is the Power Profile Kit 2. It's a Nordic development tool for current measurements and analysis. It has a range of 200 nanoamperes to 1 ampere with the resolution varying between 100 nanoampere to 1 milliampere. So this is a 10 times faster sampling rate than the first generation Power Profile Kit. So it has 100 kilosamples per second. You can use this tool to measure and analyze any embedded hardware, including all Nordic DKs, of course. It's supported by the new Power Profiler app in nRF Connect for desktop, and this new app is also supporting the old PPK. So this is a standalone product. You don't need any external hardware or anything to plug this into other than your computer. So why do developers need this? It's an easy, useful tool to track power consumption. It has support for ampere meter mode and source mode. It shows you detailed data to estimate power consumption and battery life. And you can also use it to spot and debug unwanted current drain during the entire engineering cycle. This tool or similar tools are essential if you're going to develop a low power device. So finally, we're going to demonstrate how you're going to estimate power consumption using the online power profiler and how you are going to measure power consumption using our Power Profiler Kit 2. Let us look on the online power profiler. You can find the online power profiler on DevZone, our Nordic tech support site, either through Nordic content or on the first page here, online power profiler. Here you can see the nRF52 series online power profiler and the one for nRF91 series. I highly recommend that you check out the user guide on how to use the power profiler for nRF9160, since there are very many different parameters that you should know of that may be unfamiliar for you. And all the different modes we have: RRC connected mode, idle mode, and power saving mode. As well as some SIM card settings that you should know about, and how we set up and made this calculator is very much described in this user guide. So let us click on the online power profiler for LTE. So here's the page for the online power profiler. On the top here you can select revision 1 and revision 2. So the latest version is revision 2. We're going to use that one. You can see that some parameters change here. For example, the PSM floor current goes from 4 to 2.7. And then we can select our network mode, either NB-IoT or LTM. For this demonstration, we are going to use LTM. And then we're going to enable PSM mode, power saving mode, and we are going to keep the power saving interval as is. It's also very much describes all the different parameters in the information button. Just hover over and you can see what it's about. The active time, since we are not going to use RC idle mode, we are going directly from connected mode to power saving mode. We are going to disable this. You can also see that the active mode then disappears. And when we update the different parameters, we can see that the figure on the right hand side here also updates in real time. We're going to upload some data, UDP data, to a server. Let us have it on 100 bytes. And how often we are going to send the data, we can send it, for example, each 15 minutes, so 900 seconds. And we're going to keep the TX output at 23. That's max output power. And for the RC inactivity timer and CDRX interval, CDRX on duration, CDRX inactivity timer, and IDRX PDCC age repetitions, these are typically values that you cannot change. So this is decided by the network. So to check out what these are, I highly recommend just to run the UDP sample. So let us just do that right now. Let us switch to the Power Profiler kit. So the first things that we're going to do is to open up the Power Profiler app in nRF Connect for desktop. You can find it by searching Power Profile and install if you haven't. And then you open it. So here's the Power Profiler application. We can select our device. So here we can see that I have connected my PPK2 and also have the nRF9160 DK connected to my computer. Select the PPK2 and we can see that it has default selected source meter, but you can also select ampere meter. And you can see that there's a red color here when you have source meter. This correlates to the LED on the PPK2 as well. So let's try to measure some current. Right now it's selected to source meter and I have connected the PPK to the nRF9160 DK with the correct connections. And I run the UDP sample from our nRF Connect SDK on the nRF9160 DK. Just to make sure that you connect your PPK2 to your nRF9160 DK correctly, I recommend to check the documentation on how to do this. You can find this on our documentation page, Info Center, and go to nRF Tools, PPK2, Power Profile Kit 2, and go to Setting up the Power Profile Kit. Inside there, you will see different ways of using the PPK, and I'm using this setup here today. I'm connecting the V out from the PPK2, Power Profile Kit 2, to the VDD nRF connection here. And then I have the V in from the PPK to the VDD nRF underneath there. You don't need this V in connection connected when you're using source mode. However, it's nice to have it there, since if you're going to switch between ampere mode and source mode. And you can have one ground pin to the minus pole on the external supply here. And then you have your USB connected to your computer, as well as a USB connected to your power profiling kit using the USB data power. Check out the documentation with regards to measuring power on the nRF9160 DK. This is located in nRF9160, nRF9160 DK hardware, and measuring current. I also recommend to check out our documentation page on nRF Connect SDK, so we can click it on software development kits and go to nRF Connect SDK, and we go to the top one since that's the latest one. And here we have some great documentation with regards to power optimization. Just go into application development and we see this power optimization page. Here we have an extensive guide on how you can power optimize your device. We go through how to disable logging and of course how to see this in the Power Profiler Kit tool, and how to set this in your application, different things with regards to peripherals and what you should do, and some tips with regards to cellular applications in general. We also have an example use case and also some calculations of the battery life, etc. I highly recommend to check this guide out. It's very, very helpful. First thing that I like to do is to make sure that the voltage adjustment is correct. So I usually set it at 3.7 volts or 3700 millivolts, since that's typically what we showcase in our data sheets as well. And then I like to hide the log to get a better view of the whole power profiler. The next thing that we do is just to start sampling, and then we enable power output. Now we see that the nRF9160 boots up and runs the UDP sample. We can see that we have live tracking of the power profile and the waveform, and we can disable this either by clicking this live view off or by just clicking and moving the power profile. We can also zoom in and enable and disable this lock e-axis depending on what we want to have at the topmost waveform. So let's just lock it there, and we can see on the waveform we boot up here, and straight away we do some network attach, send some data back and forth to the network, negotiate, synchronize, etc. And then we send some UDP packets to a server. The next thing that the device does is it wants to go into PSM mode. That's the default expectation of the UDP sample. So before that, you have to go into something called RC inactivity timer, and you can see that we have it around 1.4 in this sample. Let us try to see. It should be there. So it's around 1 second for this network. That is very good. Typically we see values around 5 seconds and 10 seconds. In worst case scenarios, we have seen 60 seconds. So this is very important that you find out. So now we can take these numbers and bring those into the power calculator. So if we switch to the calculator, we can now select the RC inactivity timer to, let's say, 1 second. The next thing we're going to change is this CDRX interval, and this can be found by checking one of the CDRX, two of the CDRX intervals. Then we switch back to the power profiler, zoom in on one of the CDRX intervals, and find out approximately the intervals between the events here. So it's around, yeah, let's see, about 100 milliseconds. So we go back to the calculator and set that to, yeah, let's keep it at around 128 milliseconds. That's approximately correct. And then we go to CDRX on duration. So we need to check the power profiler again, and we can see that the on duration is around 20 milliseconds, give or take 20. let's keep it at 20. So for the CDRX inactivity timer, we need to check. It's easiest to check this after the last RC connected. It's easiest to check this after a RC release. And for this little spike here, that's around where the RC release event is happening. So from there and out, it's the CDRX inactivity timer. It's around 200 milliseconds. Then we switch back to the calculator and plot that in to 200. EDRX is actually for the EDRX events in idle mode. Since we are not using idle mode now, we do not need to check this. How we can figure this out is to check it's the same as checking the CDRX on duration. So now we have quite a good estimate of this network we are on. So let's try to send some data around, let's say 200 bytes with the data transfer interval. Let's take it shorter so it's easier to see it on the power profiler. Let's see 40 seconds. So you can have the power saving mode for several hours. However, you can wake up from the power saving mode whenever. So the nice thing with this figure here is that you can go into each event and see what everything is doing and compare that with the real measurement. So we can see that we begin with the network sync, then we have the SIM sync, and we have the RC setup reconfiguration, and you can also see approximately how much current you're using in these different events. Then we go to the tracking area update, and then of course the data upload to your server, and then we go into this DRX inactivity timer, and then we get these CDRX events and CDRX idle in between these events. And this keeps going until we get this RC release. And then we have the CDRX inactivity timer again before we jump into PSM. So we can see that the total average current for this setup here is around 1.31 milliamperes. So now we can actually export these settings. And these settings is exported into a JSON file, and we can save these settings, and then you can import the settings and get the same parameters. So you can save a huge list of different networks. We also have some presets already, so we can select here in this drop-down menu. And this online power profiler has this export NCS project config. So it actually exports the different parameters that you can add into the UDP sample. This is mainly the requested periodic tau, if you're going to use RC idle mode, and how much data you're going to send. So here is the file that the online power profiler made for us. We can see that we have the upload frequency for 40 seconds, sending 200 bytes, selecting LTLM, and etc. We just copy the whole thing, go into udp and project.com file, and the last parameters we switch out with these new ones. We save, and then we build and flash using the West tool. You can use Sega Embedded Studio, of course. Just do the same thing, add the parameters in the project.com file, and build and run as usual. So here you see the power profiler kit again, and we are doing the power measurements. And let's just keep this running for a while and capture the average current. So now we have captured the power profile for 2 minutes. We can see it here in the time here, 2 minutes. And this is the network attached, and then we have 40 seconds between each each event here. So you can see from this, the device goes to sleep, PSM mode. So we see an average current of 2.7, and then for the next event, it's for around 40 seconds, and then you send some UDP data again, go into RRC inactivity timer, and then go to sleep again. And we see the PSM current around 2.7 here as well. So this is as expected. So let us see approximately the total average current. So the total average current is 1.05 milliamperes for this testing here. And let's look at the power calculator again. The measured total average current was 1.05 milliamperes. However, our estimation of the total average is around 1.31 milliamperes. The reason is that the estimation is higher is most because this TX output power is set to 23 dBm. This is max output power. This is typically when you have very bad coverage. However, where I'm sitting quite close to a base station, so I have good coverage. So let us take it down to 0 dBm and see if we are closer to our measured current. And here you can see that the total average current is estimated to be 1.09 milliamperes. That's very close to 1.05 milliamperes. So the estimated current and the measured current is very similar. So this demonstration was a success. So let's get back to the presentation. How to optimize for low power. So the most important point, I think, is that you need to get to know your network, get to know the different parameters that the network decides, and then the different parameters that you cannot configure, and also check which parameter you can configure and is approved by your network. And also highly recommend that you estimate power consumption and play around with the online power profiler. Try to just change different parameters, see what changes the power consumption, the average current, etc. And then, of course, go out and measure the power consumption. Now we have the Power Profiler Kit 2, which makes this really easy. Just to bring it in your pocket and go out in the field with a nRF91DK or a custom nRF91 board, and then measure the current on the network and your application. I also recommend that you know the different protocols and the cellular technology you are going to use, since there are some that are more suitable than others based on your application. So for example, you have MQTT, CoAP, and LWM2M that has different use cases, and some are better than others. Also LTM and NB-IoT. LTM is more suited for asset tracking, for example, because it has inbuilt support for mobility and has higher throughput. And with regards to applications that you have in basements, for example, underneath concrete, you can have a power meter underneath in a basement, and then it's best with NB-IoT, for example, because it has better penetration. For the application side, it's very important that you sleep as much as possible and disable the peripherals when they are not needed, and also turn off logging, of course. If you see around 500 to 700 microamperes in your power profiling, and this is typically the UART still being on, so the logging is not turned off, for example. I highly recommend that you check out our power optimization guide on our NCS website, nRF Connect SDK website documentation page, because this is a very extensive guide. It shows you point by point how to use the Power Profiler Kit 2 with the online Power Profiler. It sets up some scenarios for you, and it also shows you how to calculate the battery life of your device. And some other things that you need to think about is, for example, for edge computing, you need to send information and not data. What we mean by this is you have an application with an accelerometer sensor on board, and instead of sending all this data continuously, you turn on the radio, use a lot of current, and it stays on for a long time because you have to send all this data. But instead, send the information. So you do a little processing on the application side, that you see that the thing fell over sideways hard and is now laying flat, and you can send this one event instead of all this data. So you just wake up, send this data, and go back to sleep again. So for optimizing power, we have several documents on our website, and also a lot of great discussions on DevZone, so please visit those sites. And if you have any more questions with regards to this, I highly recommend to also go on DevZone and make a ticket there. Now it's time for questions and answers.